There is a long-standing tradition within Christianity of reading Daniel 9's 70 weeks as a messianic prophecy fulfilled in Jesus Christ. The 70 weeks of years, with each prophetic day counted as one solar year, are divided into three groups: a 7-week period spanning 49 years, a 62-week period spanning 434 years, and a final period of 1 week spanning 7 years. The 7 and 62 weeks are most frequently understood for the purpose of Christological interpretation as consecutive, making up a period of 69 weeks or 483 years, beginning with the decree given to Ezra by Artaxerxes I in 458 or 457 BC, and terminating with the baptism of Jesus in 26 or 27 AD. The reference to an anointed one being cut off in verse 26 of Daniel 9 is identified with the crucifixion of Jesus and has traditionally been thought to mark the midpoint of the 70th week or 3.5 years, causing many to conclude that Christ was crucified anywhere between 29 to 31 AD. Another influential way of reading the prophecy follows Africanus in identifying the warrant given to Nehemiah in 445 or 444 BC as the starting point. 483 solar years from 445 or 444 BC would extend somewhat beyond the lifetime of Christ to 39 or 40 AD. Hence, some Christological interpretations reduce the period to 476 years by viewing the 483 years as biblical years, with each biblical year having only 360 days. The 69 weeks of prophetic years are then considered to terminate with the death of Christ in 32 or 33 AD. I would like to point out that these two interpretations of Daniel's 70 weeks prophecy used two starting points in making their calculations, namely the decree given to Ezra by Artaxerxes I in 458 or 457 BC, and the warrant given by Artaxerxes I to Nehemiah in 445 or 444 BC. Now, according to Ezra chapter 7, the decree given to Ezra happened in the 7th year of Artaxerxes I, while according to Nehemiah chapter 2, the warrant given to Nehemiah was in the 20th year of Artaxerxes I. Therefore, the validity of Daniel's 70 weeks interpretation and calculation lies heavily in the accuracy of the dating of Artaxerxes I's reign, which according to Ptolemy's Canon of Kings was from 464 to 424 BC. But what if this historical dating is wrong? In this video, I will show you why it actually is so. Those who claim that the Persian chronology of the reigns of Achaemenid kings are accurate to the year point to astronomical diaries as their proof. One such diaries are the Babylonian Astronomical Diaries, abbreviated BM, and currently stored in the British Museum. They are a collection of Babylonian cuneiform texts that contain systematic records of astronomical observations and political events, as well as calculated predictions based on known planetary motions. The Venus Tablet of Amisaduqa, abbreviated VAT, is the record of astronomical observations of Venus, as preserved in numerous cuneiform tablets dating from the 1st millennium BC. It is believed that this astronomical record was first compiled during the reign of King Amisaduqa of the 1st dynasty of Babylon. However, relying on astronomical diaries for dating events and rains can prove to be misleading, especially since planetary movements are cyclical and their exact relative positions can be repeated over a period of time. Let me highlight one such astronomical observation that was misinterpreted, miscalculated, and erroneously used for dating Artaxerxes I's reign. BM 33478 is dated to a king named Artaxerxes. The regnal year is partially broken. Hunger tentatively dated it to the 24th year of Artaxerxes I, 442 to 441 BC, but he admitted that both the date and the identity of the king are problematic. The problems were solved a few years later by Johannes Koch, who demonstrated that the tablet belonged to the 23rd year of Artaxerxes II, 382 to 381 BC instead. This conclusion was later supported by R.J. van der Spek. As you can see from this example, Babylonian tablets do not use appellations such as the first or the second for the king's name, so that Artaxerxes II can be easily misidentified as Artaxerxes I by modern scholars. Now, I believe Artaxerxes I's reign was dated at least 2 years too early, as were the reigns of other Achaemenid kings as well, like Xerxes I, for example. Let me show you why. Herodotus mentioned a solar eclipse that occurred at the start of the Second Persian invasion of Greece. According to historians, the invasion began in the spring of 480 BC when the Persian army led by Xerxes I crossed the Hellespont. Eclipses during the War of Xerxes with the Greeks by Lin. In the seventh book of Herodotus, where he says that in the early spring, whilst Xerxes was at Sardis preparing to set out on the Grecian expedition, the sun, leaving his seat in heaven, became invisible, and instead of day, it became night. The date when this expedition took place is considered to have been one corresponding to 480 BC. No eclipse of the sun, however, could have been visible in Western Asia during the spring of that year. Take note, instead of admitting that their calculated date for the Persian invasion of Greece was wrong, historians would rather blame Herodotus by saying Herodotus had the sequence of events wrong. Now, before I use Stellarium software to analyze the eclipse mentioned by Herodotus, let me discuss in detail one important factor in calculating eclipses that occurred in the distant past, namely the algorithm of delta T. NASA Eclipse website. The orbital positions of the Sun and Moon required by eclipse predictions are calculated using terrestrial dynamical time (TD) because it is a uniform time scale. However, world time zones and daily life are based on universal time (UT). In order to convert eclipse predictions from TD to UT, the difference between these two time scales must be known. The parameter delta T is the arithmetic difference in seconds between the two, as delta T equals TD minus UT. Past values of delta T can be deduced from the historical records. In particular, hundreds of eclipse observations, both solar and lunar, were recorded in early European, Middle Eastern, and Chinese manuscripts and canons. In spite of their relatively low precision, these data represent the only evidence for the value of delta T prior to 1600 AD. In the centuries following the introduction of the telescope, circa 1609 AD, thousands of high-quality observations have been made of lunar occultations of stars. The average annual change of delta T was 0.99 seconds from 1965 to 1980. Future changes and trends in delta T cannot be predicted with certainty. Extrapolations from the table, weighted by the long period trend from tidal breaking of the moon, offer reasonable estimates. Outside the period of observations, 500 BC to 2005 AD, the value of delta T can be extrapolated from measured values using the long-term mean parabolic trend. Historical records affect the precise determination of past values of delta T prior to the introduction of the telescope circa 1609 AD. And quite obviously, the calculation of delta T is biased towards how modern historians date past eclipses. And as for the effect of the tidal breaking of the moon, it is parabolic in nature, meaning it varies regularly over a period of time, just like the moon's distance varies from apogee to perigee regularly. In my discussion of historical eclipses, I will be using two algorithms of delta T, namely JPL horizons and Chaperon-Tooze and Chaperon 1991. And I will be switching between these two algorithms from time to time. Now using Stellarium and setting the algorithm of delta T to JPL horizons and the date to February 17, which was early spring of 478 BC or negative 477 in astronomical year numbering, and at 10:19 UTC, one can see an annular solar eclipse which was visible in Abydos or the Hellespont at 40 degrees 11 minutes 43 seconds north, 26 degrees 24 minutes 18 seconds east. The time of maximum eclipse occurred just 13 minutes before culmination at local noon, with an eclipse obscuration of 89.4%. I believe this is the solar eclipse that occurred at the start of the second Persian invasion of Greece as recorded by Herodotus. This 2 years error in the Persian chronology, which wrongly dated the start of the second Persian invasion of Greece to 480 BC instead of 478 BC, is further confirmed by the way historians dated the short-lived Babylonian revolts of two rebel kings of Babylon, Bel-Shimani and Shamash-Eriba, sometime during Xerxes I's reign, which is believed to be from 485 to 465 BC. The near universally accepted date for the start of this revolt is in July 484 BC on the fourth month of Xerxes I's second year as king. The revolt lasted for 3 months only. However, those years during Xerxes' reign, when there are no known Babylonian tablets mentioning Xerxes, who was unseated briefly by the rebel kings, were also considered as possible dates for this 3 months rebellion. And these years are 484 BC, 479 BC, 477 BC, 475 BC, 473 BC, 472 BC, 468 BC, and 466 BC. So basically, the year of the revolt could have happened anytime in the 2nd, 7th, 9th, 11th, 13th, 14th, 18th or 20th year of Xerxes I's reign. Dating the reigns of Xerxes and Artaxerxes by Gerard Gertou, pages 47 to 48. A chronicle fragment BM 36304 and an astronomical fragment enable the dating of these Babylonian revolts. Although the data are fragmentary, they describe a revolt dated during Xerxes' reign. The astronomical fragment reads, "The month of Tammuz, the 5th day, to Babylon went the troops of Elam. Mars into Cancer entered." Lines 6 to 7 of the astronomical fragment dated Xerxes I's military response to the Babylonian revolts in a year when Mars entered Cancer on the 5th day of the 4th Hebrew month of Tammuz, which is also the 4th Babylonian month of Dumusu. So the question is, which day of the year in 484 BC, the near universally accepted year for this 3 months long revolt, did Mars enter Cancer? Note that Mars' synodic orbital period is about 2 years and 49 days, so that Mars can be seen entering Cancer only about once every 2 years. Using Stellarium and setting the algorithm of delta T to JPL horizons and the date to August 27 of 484 BC or negative 483 in astronomical year numbering, one can see that Mars entered Cancer around 2:14 UTC in Babylon using coordinates 32 degrees 32 minutes north, 44 degrees 25 minutes east. Now August 27, 484 BC Julian calendar corresponds to the 8th day of the 6th Hebrew month Elul, or the 6th Babylonian month Ululu, and not the 4th Babylonian month of Dumusu, as stated by the tablet. Evidently, 484 BC could not have been the year of the Babylonian revolt. However, on July 3, 463 BC Julian calendar at about 2330 UTC, Mars entered Cancer coming from Gemini when the moon was 5.5 days old on the 4th Hebrew month of Tammuz, or the 4th Babylonian month of Dumusu, just as described in the astronomical fragment. Now, since the currently accepted year of Xerxes' death is 465 BC, this means the Persian chronology currently used by historians and Bible scholars is at least 2 years too early. Also, later in this video series, you will find that I dated Xerxes I's 20th year as 463 to 462 BC. If you still recall, one of the candidate years for the Babylonian revolt was Xerxes I's 20th year, and this matches my July 3, 463 BC dating for the astronomical fragment about the revolt. Furthermore, according to my revision of the Persian chronology, Xerxes I, who ruled 21 years, died in 461 BC, or 4 years later than the historical date in 465 BC. Now, I would like you to remember that Xerxes I's death could not have happened earlier than 463 BC, the correct year of the Babylonian revolt, because current Persian chronology uses the astronomical tablet BM 32234 to prove that Xerxes I died in 465 BC, which I have just shown is an impossibility. For me to properly correct and recreate the Persian chronology, I have to have other anchor dates supported by astronomical observations in addition to just identifying the date of the solar eclipse that occurred at the start of the second Persian invasion of Greece and the date of the Babylonian revolts. So in this presentation, I will be discussing the following recorded astronomical observations which I will date according to my own personal interpretations. Number 1. The lunar eclipse dated the second year of Nabonidus' reign or slightly before and described in Nabonidus number 18, a cylinder inscription which was discussed by Paul Alain Beaulieu in page 127 of his book, The Reign of Nabonidus, King of Babylon, 556 to 539 BC. Number 2. The solar eclipse that occurred during the reigns of Astyages of Media and Alyattes of Lydia, as mentioned by the Roman philosopher Marcus Tullius Cicero in his work Divination, and by Pliny the Elder in Book 2, paragraph 9 of his work Natural History. Number 3. The solar eclipse predicted by Thales of Miletus, which occurred during the war between Cyaxares of Media and Alyattes of Lydia, as recorded by the Greek historian Herodotus in his book The History. This war is also known as the Battle of Halys, as some scholars assume the location of this battle was near Halys River, which was located in the border region between both kingdoms at that time. Number 4. The astronomical tablet referred to by three names, STRM Cambis 400, LBAT 1477, and BM 33066, that contains the astronomical data of the 7th year of Cambyses II, successor of Cyrus the Great. Number 5. The astronomical tablet BM 32234 used for dating the death of Xerxes I, according to Matthew Olsen-Richver in page 152 of Xerxes and Babylonia, the Cuneiform Evidence. This tablet reports two eclipses, a lunar eclipse in the region of the four rear stars of Sagittarius on month 3 of the year of death of the king who died on month 5, and another lunar eclipse on month 8 of the year of death of the same king. In this video, I will show that this tablet is not about Xerxes I being killed by his son as interpreted by scholars, but rather about Artaxerxes I, who was killed by his son Xerxes II. Number 6. Several Babylonian tablets dating the ascension year of Darius II to the 41st year of Artaxerxes I. Number 7. The solar eclipse that occurred early summer of the 8th year of the Peloponnesian War. And according to the Athenian historian Thucydides, Artaxerxes I died in the 7th year of this war. Number 8. The lunar eclipse that occurred in the summer of the 19th year of the Peloponnesian War. Number 9. The solar eclipse that occurred in the summer of the first year of the Peloponnesian War. Number 10. The astronomical tablet BM 71537 that mentions a lunar eclipse when Artaxerxes III sat on the throne, and also a solar eclipse when Artaxerxes III died in year 21 of his reign. Number 11. The astronomical diary VAT 5047 that preserves information about two lunar positions relative to the positions of Mercury, Venus, Jupiter, and Saturn, and which, according to Carl Olof Johnson in his work The 20th Year of Artaxerxes and the 70 Weeks of Daniel, is clearly dated to the 11th year of Artaxerxes I, or specifically 454 to 453 BC historically. Number 12. astronomical tablets LBATS 1387, 1388, and 1486, published as number 56 in Hunger's Astronomical Diaries and Related Texts from Babylonia, abbreviated ADT, Volume 5, which contain dated observations of the planet Venus during the 7th, 15th, 23rd, 27th, 31st, 35th, and 39th year of an unnamed king and the 6th year of his successor. According to Carl Olof Johnson in his work, The Litmus Test of the Absolute Chronology, the unnamed king and his successor were Artaxerxes I and Darius II, respectively. Furthermore, according to Johnson, the observations recorded for year 7 in months 1 to 6 all fit the 7th year of Artaxerxes I, or 458 BC. However, in this video series, I will show that the unnamed king was Artaxerxes II and the successor was Artaxerxes III instead. Number 13. The astronomical tablet LBAT 1393, transliterated and translated by Abraham Sachs and Hermann Hunger and published as number 54 in their book ADT Volume 5, pages 158 to 165, which records observations of the planet Jupiter dated to years 8, 19, 20, 31, and 32 of an unnamed king. This was dated for the reign of Darius I, according to Carl Olof Johnson in his website titled Chronology Persia, Puruli's response to Carl Olof Johnson examined. There are many other astronomical tablets used by scholars to date Persian chronology, but there are too many for me to discuss all of them. However, I believe the tablets which I will be discussing in this 11-part video series will suffice to prove the point I am making, and this is to show that, number 1, planetary movements are cyclical, and their exact relative positions can be repeated over a period of time. And this means astronomical positions which scholars believe happened in the reign of one king can repeat itself in the reign of another king. And errors in dating can happen in this case if the tablet does not mention the name of the king or the name is unreadable. Number 2. Names of kings do not have appellations, so that the Artaxerxes mentioned in a tablet can refer to Artaxerxes I, or the second, or the third, and so on. I already showed one case when scholars previously applied an astronomical tablet to Artaxerxes I when it should have applied to Artaxerxes II instead.